Humans and immortality. The assertion that humans are immortal, indestructible, is a profoundly counterintuitive statement when juxtaposed with the ubiquitous, visceral experience of biological senescence and ultimate somatic dissolution we term death. Yet, when viewed through the lens of fundamental physics and cosmic chemistry, the premise shifts from a philosophical conundrum to an almost tautological observation. The human body, this complex, exquisitely organized structure we inhabit and identify with, is, at its most irreducible level, a vast, dynamic constellation of atoms. These constituent particles, the fundamental building blocks governed by the laws of thermodynamics and conservation, do not simply cease to exist upon the cessation of biological function. When the intricate choreography of cellular respiration, enzymatic catalysis, and neuronal firing finally collapses, the moment we label as death, the atoms that comprised the flesh, bone, and neural network do not vanish into a void. They are merely reorganized, redistributed, incorporated into the ceaseless cycle of elemental transformation that underpins the entire material universe. Thus, to posit human immortality is not a statement of eternal individual subjective experience, but rather an affirmation of material persistence. We are merely transient arrangements of cosmic dust destined for subsequent, equally transient arrangements. To ground this abstract concept in tangible reality, let us examine a commonplace, yet chemically profound, aspect of our physical being, the color of human blood. Why is it red? The immediate, textbook answer, drilled into generations of secondary school students, rests upon the presence of a substantial concentration of the element iron. Specifically, it is the iron atom, sequestered within the heme prosthetic group of the hemoglobin molecule, that imparts this characteristic coloration. Hemoglobin, a complex metalloprotein, acts as the principal oxygen-carrying agent in vertebrate circulatory systems. The ferrous ion, the iron atom in its 2+ oxidation state, possesses electronic configurations that selectively absorb light in the blue-green spectrum, resulting in the reflected light appearing red. Consider the counterfactual scenario suggested by the premise: if, hypothetically, the evolutionary pressures or the ambient environment had favored a molecule utilizing a different transition metal in place of iron for oxygen transport, say, copper, what would be the resultant color of our circulatory fluid? The immediate conclusion, following the same principles of light absorption and reflection governing the chromophores in other biological systems, such as the blue hemocyanin found in the circulatory systems of many mollusks and arthropods, dictates that our blood would indeed appear blue. Copper, when complexed in certain coordination geometries, exhibits absorption spectra that favor the transmission of blue light. This simple chemical thought experiment underscores the dependency of our observable biological traits on the available elemental palette. This leads directly to the more fundamental query that drives the selection of elements in biological construction: nature's choice of iron. Why was iron selected as the primary metallo-component for life's most critical transport mechanism on Earth, rather than, perhaps, a more chemically versatile element like titanium or a lighter metal like magnesium, which plays a crucial role in chlorophyll? The answer, as the initial conjecture posits, is deceptively simple. Iron is the most abundant metallic element available in the terrestrial environment where life, as we know it, originated and evolved. This abundance translates directly into accessibility and energetic favorability for the nascent biosystems that required robust, efficient means of resource utilization. While elements like silicon or oxygen might be vastly more abundant overall on the planet's crust, when restricted to the domain of metallic elements capable of forming the necessary coordination complexes for reversible oxygen binding, iron holds the distinct advantage on Earth. However, to truly appreciate the context of this choice, one must expand the frame of reference beyond the terrestrial surface. The inquiry deepens when we consider the cosmic inventory. While aluminum might rival or even surpass iron in certain localized planetary crustal surveys, the overarching, universal truth regarding elemental abundance shifts dramatically. In the cosmos as a whole, after hydrogen, the undisputed king of elemental presence, and helium, the next most abundant species, iron occupies a singular, critical position among the heavy elements. Stellar nucleosynthesis, the grand furnace of the universe, dictates this reality. Elements up to iron, specifically isotopes such as iron-56, are formed through fusion processes in the cores of massive stars. Fusion beyond iron becomes energetically unfavorable. It requires an input of energy rather than releasing it. Consequently, the creation of elements heavier than iron, such as gold or uranium, generally requires the catastrophic energy release of supernovae or neutron star mergers, events far rarer and more violent than the steady fusion that builds up to iron. Therefore, the stellar remnants, the nebulae from which subsequent generations of stars and planets, including our own solar system, coalesce, are inherently richest in iron among the metals. Since the material constituents of the human body, the hydrogen, carbon, oxygen, and yes, the iron, were forged in the hearts of long-dead stars and dispersed across interstellar space before being incorporated into the accretion disk that formed Earth, it is logically consistent that the most pervasive metallic building block available to terrestrial biochemistry would be the one most richly supplied by cosmic recycling, iron. Our biology is a direct inheritance from the galactic environment, perfectly optimized for the raw materials it found in abundance. At this juncture, the conceptual landscape broadens, and the initial startling assertion begins to gain a compelling, scientific resonance. The entire observable universe, governed by quantum mechanics and general relativity, is a closed, or at least a contained, system composed of a finite, albeit staggeringly large, inventory of fundamental elements listed on the periodic table, ranging from the primordial hydrogen to the synthesized superheavy elements. These elements, the irreducible constituents, arrange and rearrange themselves according to probabilistic laws and available energy states. Everything that exists, the gaseous giants, the molten core of our planet, the intricate crystalline lattice of a diamond, and yes, the exquisitely complex, self-replicating, information processing system we identify as a human being, is nothing more than a temporary configuration of these atoms. A collection of atoms assembled, at time instance $t sub 1, into the specific arrangement that constitutes U, reading these words, possesses a certain set of quantum states, chemical bonds, and spatial orientations. If, at the very next infinitesimal moment, time instance $t sub 2, the forces governing molecular interaction shift, perhaps due to rapid environmental perturbation, or more naturally, through the gradual, inexorable process of biological degradation and elemental exchange, that specific arrangement dissolves. The carbon atoms that formed your neuronal microtubules might quickly bond with atmospheric oxygen to form carbon dioxide, destined to be absorbed by a nearby photosynthetic organism. The iron atoms that powered your oxygen transport might become oxidized and incorporated into the soil matrix, perhaps eventually forming a component of a basaltic rock formation miles away. The hydrogen and oxygen atoms that comprised your water content will eventually disperse into the hydrological cycle. Crucially, the atoms themselves have not been destroyed. Their inherent mass energy, as described by Einstein's celebrated equivalence, $E equals $m times $c squared, remains conserved within the system. The constituent particles, protons, neutrons, and electrons, continue their existence, albeit in a new structural context. That arrangement, momentarily identified as a human, is gone, but the elemental substrate persists. The next instant, those same atoms might coalesce, following the dictates of chemistry and physics, to form the distinct molecular structure of a canine, a fleeting optical distortion we label a shadow, a temporary absence of photons interacting with matter, or the intricate cellulose structure of a flowering plant. In this fundamental, reductionist sense, the supposed ontological divide between living and non-living, between human and inanimate matter, dissolves into a spectrum of complexity and temporary organization. We are not fundamentally distinct from the rock beneath our feet or the nebula light years away, we are merely a more intricate, self-aware manifestation of the same underlying material reality. Life, therefore, becomes a highly specialized, temporary thermodynamic process, a localized, improbable decrease in entropy maintained only through a constant throughput of energy drawn from the environment. Death, consequently, is not an absolute annihilation of the self or the constituent parts, but rather the termination of that specific, high-energy, self-sustaining organizational pattern. Life and death are relative descriptions applied to the persistence and rearrangement of matter, not absolute verdicts on the existence of the atoms themselves. This cosmic accounting allows us to approach the theory of human immortality not as a fantastical denial of mortality, but as a necessary consequence of universal conservation laws applied to biological structure. The human experience, the sum total of our memories, personalities, and subjective realities, is encoded within the specific patterns of neural connectivity, the synaptic weights, the dendritic spines, the precise arrangements of proteins within trillions of neurons. When the biological machinery fails, this informational structure is disrupted. Yet, the atoms themselves are liberated to seek new stable configurations. The most significant, and indeed the only truly stubborn, remaining aperture for debate within this physicalist framework centers on the phenomenon of human consciousness. This is the ultimate loophole, the most vexing problem that resists clean reduction to mere atomic rearrangement, the hard problem of consciousness, as articulated by philosopher David Chalmers. How does the specific, 3-pound mass of electrochemical activity occurring within the skull give rise to the subjective, qualitative experience, the qualia of seeing the color red, feeling grief, or contemplating one's own material persistence? If consciousness is purely an emergent property of complex information processing within the biological substrate, a functional state achieved only when the particular architecture of the living brain is maintained, then the dissolution of that architecture at the moment of somatic death implies the absolute cessation of that subjective experience. The atoms disperse, and the unique configuration that generated you vanishes forever, leaving only the raw material to form a flower or a stone. In this scenario, the immortality of the atoms is undeniable, but the immortality of the self, the feeling of being me, is extinguished as thoroughly as a single candle flame extinguished by a sudden gust of wind. The atoms that constituted the flame remain as heat and smoke, but the light and the specific flicker are gone. However, the allure of the immortality hypothesis persists because the nature of consciousness remains stubbornly resistant to definitive mechanistic explanation. Modern neuroscience has made staggering advances in correlating brain activity with specific conscious states. Functional magnetic resonance imaging, or fMRI, allows researchers to map increased blood flow, and thus increased metabolic activity, to areas like the dorsolateral prefrontal cortex during executive function, or the amygdala during emotional processing. Data from large-scale neuroimaging projects, often involving hundreds of thousands of subjects, confirm incredibly robust correlations between specific neurological configurations and specific conscious reports. For instance, studies involving patients recovering from severe anoxic brain injury often show that recovery of complex cognitive functions correlates directly with the observed structural and functional connectivity returning to baseline, suggesting a physical basis for the self. Yet, correlation is not causation in the most fundamental sense. We do not yet possess a verifiable, first-principle theory linking the firing rate of a specific ensemble of neurons, say, 10,000 C fibers, to the specific, agonizing feeling of intense pain. This explanatory gap, the gulf between the objective, third-person description of neuronal firing and the subjective, first-person reality of experience, is what keeps the door ajar for non-reductive theories of consciousness. Could consciousness, rather than being solely an emergent property of this specific biological arrangement, be a more fundamental property of matter itself, perhaps linked to quantum coherence or information density? Theories proposing panpsychism in its various forms suggest that consciousness, or proto-consciousness, is a feature inherent in all matter, even at the atomic or subatomic level. If this were true, then the dispersal of the constituent atoms of the brain does not imply the disappearance of consciousness, but rather its instantaneous dilution back into the universal substrate. The highly ordered, complex consciousness of a human being would revert to the incredibly low-level, rudimentary forms of experience inherent in individual particles. When the atoms reassemble into a dog or a flower, those new configurations might generate their own complex, yet different, forms of subjective awareness, each built upon that universal, fundamental substrate of experience. The individual pattern is lost, but the potential for experience remains woven into the fabric of reality. Furthermore, emerging research in areas like quantum biology hints at processes that may not be fully captured by classical biochemistry. While highly speculative and subject to intense scrutiny, studies exploring phenomena like quantum entanglement or quantum tunneling in biological processes, such as enzyme action or even microjoule dynamics within neurons, raise the possibility that consciousness might leverage non-classical physical mechanisms. If the integrity of the self is tied to a specific, non-local quantum state, a coherence field, perhaps, the physical destruction of the brain might lead not to cessation, but to decoherence. The organized wave function collapses back into the vast ocean of universal quantum possibilities, waiting for another opportunity to condense into a complex informational structure. consider the implications of high-energy physics on elemental persistence. We know from particle accelerators that under extreme energy regimes, matter can be transformed into energy and then reformed into entirely different particles. Protons can become neutrons, electrons can become neutrinos, though the total baryon number and lepton number must be conserved overall. Death, though a low-energy affair compared to the Large Hadron Collider, is a process of constant, albeit lower energy, transformation. The energy released during the decomposition of organic molecules is what fuels the heat dissipated by a decaying corpse, driving the local entropy of the immediate surroundings up while enabling the atoms to seek new, lower energy states. If we accept the premise that all matter is immortal in its constituent parts, the question becomes one of informational persistence. The individual self is a sophisticated piece of data storage and processing. Death is the catastrophic hardware failure. Immortality, under the atoms are forever model, requires either a. the information to be successfully uploaded or transferred before hardware failure, or b. the information to be somehow inherent in the base matter itself, independent of the specific hardware configuration. Scenario A leans into technological futurism, the realm of mind uploading, digital persistence, or substrate-independent minds. Current neuroscientific mapping techniques, such as connector mix, aim to map the entire structural wiring diagram of a brain, the Human Connectome project being a monumental step in this direction, detailing the structural connections between billions of neurons. While mapping the physical connections is an achievement, it is still vastly incomplete. The functional reality of consciousness is not just in the wires, but in the dynamic state of the synapses, the precise strength of the chemical signals, the receptor densities, the modulation by neuromodulators. Even if we could scan and digitally replicate the static structure of a brain down to the molecular level, would the resulting simulation be the original consciousness, or merely a perfect, non-experiencing echo? This relates directly to the Chinese room argument, syntax without semantics. The challenge is replicating the dot process, not just the architecture. Scenario B, the philosophical angle supported by the persistence of atoms, suggests that the subjective spark is not entirely dependent on the specific configuration, but rather a universal feature that becomes highly organized in the human brain. If true, then when the human configuration breaks down, the basic constituent experience remains, simply becoming disorganized. This resonates with the ancient Stoic idea of a universal reason or logos, pervading all things, or indeed, the Buddhist concept of interconnected emptiness from which all forms arise and to which all forms return. The atoms that formed one person's unique awareness return to the undifferentiated field of cosmic potentiality, ready to form the next configuration, be it a worm or a star. Let us delve deeper into the probabilistic mechanics of atomic survival and reassembly. The universe operates on timescales that dwarf human history. The half-life of a proton, while incredibly long, estimated by some grand unified theories to be upwards of 10 to the power of 34 years, is still finite, though practically infinite for the purposes of human consideration. For the atoms that constitute us, the immediate fate is determined by terrestrial geochemistry and biology. Consider the timescale of biological recycling. A carbon atom in a protein might cycle out of the body within days or weeks. An atom in the calcified matrix of the femur, however, might remain sequestered for centuries before being released through geological weathering or erosion. The concept of reincarnation under this strictly physical model translates to the reincorporation of these elements into a new biological entity. The probability of any given collection of atoms, say, the exact arrangement that forms the unique molecular fingerprint of your left retina, reforming into the exact same functional configuration of a living being in the next terrestrial cycle is astronomically small, effectively zero on any meaningful timescale shorter than the eventual heat death of the universe when all organized matter degrades into a uniform soup of fundamental particles. The sheer combinatorial space of possible molecular arrangements for a structure as complex as the human brain is far too vast for random thermal fluctuations to recreate the precise memory pattern of you. However, the identity derived from the aggregate of elements is not contingent on perfect replication. If the atoms that comprised a human's liver are now in a rainforest canopy, and those that formed the human's ear are now in deep ocean sediment, they are still immortal in the sense that they exist. The tragedy of death, from this perspective, is the irreversible loss of the specific, organized dot information. That defined the unique pattern, not the loss of the raw material. This leads us to confront the paradox: if the atoms are immortal, why do we universally experience death as a definitive end? Because the specific, self-referential informational structure we call consciousness requires continuous maintenance energy, a constant supply of low-entropy resources, and an intact, active processing unit. The brain is a highly optimized, parallel processing device that runs on glucose and oxygen. When the energy input stops, the system rapidly succumbs to the second law of thermodynamics, its complex organization dissolving into higher entropy states: decay, decomposition, dispersal. The academic pursuit of biological immortality, often termed radical life extension or achieving negligible senescence, focuses on repairing or indefinitely sustaining this biological hardware. Research into telomere attrition, the accumulation of somatic mutations, the buildup of lipofuscin waste products, and the dysregulation of cellular signaling pathways, all hallmarks of aging, is an attempt to artificially extend the operational lifespan of the dot pattern. If scientists, utilizing tools derived from molecular biology like CRISPR-Cas9 for precise genomic editing, or senolytic drugs designed to clear out aged, dysfunctional cells, can indefinitely postpone system failure, then the subjective experience of selfhood is extended, perhaps indefinitely, within the confines of the biological machine. This is not cosmic immortality, but prolonged functional existence. Major biotechnology firms and academic labs are aggressively pursuing pathways to effectively halt or reverse the aging process, driven by the understanding that aging is not an immutable law, but rather a collection of engineering problems that have yet to be solved. Current data on model organisms, such as genetically modified nematodes or mice exhibiting significantly extended lifespans, sometimes doubling their normal longevity, suggest that the biological programming for indefinite maintenance might indeed exist, merely requiring the suppression of accumulated damage. Yet, even if biological decay were perfectly solved, if cellular repair mechanisms ran perfectly forever, the material body remains subject to external, non-biological threats, accidents, catastrophic environmental shifts, or cosmic events. A perfectly maintained human body, still composed of atoms, could be vaporized in a high-energy collision or incorporated into a black hole singularity. In those instances, the ultimate fate of the constituent atoms is far more dramatic: reorganization, perhaps even transmutation into exotic forms of matter or energy, but persistence remains the final law. The most profound implication of the materialist view of immortality, that we are merely transient arrangements of cosmic stuff, is the profound shift it mandates in our perception of value and attachment. If the atoms comprising a beloved individual are destined to become part of the soil, the atmosphere, or a distant star, the emotional weight shifts from mourning the dot disappearance of substance to appreciating the dot rarity and complexity of that specific configuration. The value resides in the ephemeral pattern, the brief, miraculous organization of iron and carbon that achieved self-awareness and expressed love or creativity. The continuing mystery of consciousness, however, acts as a persistent philosophical anchor, pulling us back to the subjective realm where the atomic theory feels insufficient. If consciousness is strictly non-physical, a view held by dualists, then the dispersal of the atoms at death means the non-physical entity is simply released from its physical tether, potentially moving to an immaterial plane or dissolving into a universal, immaterial field. This would imply a form of consciousness immortality distinct from atomic immortality. However, the vast majority of contemporary scientific endeavor operates under the assumption of physicalism, seeking explanations entirely within the laws governing mass, energy, and information. Recent breakthroughs in theoretical physics, while grappling with the entanglement of quantum gravity and general relativity, have not yet provided any empirical evidence for a non-material substrate that can survive the complete physical disintegration of the organism. In conclusion, the initial hypothesis stands firm when examined through the lens of conservation laws. Humans, as configurations of atoms, are immortal because the atoms that compose them are not destroyed upon death. They are recycled, participating in the endless cosmic exchange, eventually forming a dog, a shadow, or a flower, depending on environmental probability and thermodynamic necessity. Life and death are not absolute states of being or non-being for the fundamental constituents, but rather relative descriptors for the temporary state of complex organization. The only true unknown, the scientific frontier that holds the key to whether our subjective experience is immortal, lies in fully elucidating the mechanism by which physical matter generates qualia, the genesis of consciousness from inert particles. Until that final loophole is closed with demonstrable, repeatable evidence, the physicalist must concede that while the atoms endure, the conscious self, as we currently understand it, is irrevocably subject to the dissolution of its temporary, beautiful, and fleeting arrangement. The atoms are eternal, the moment is precious precisely because it is transient, destined for a new form, a new iteration in the universe's boundless, material story. The continuation of the physical substrate is a certainty, the continuation of the perceived self remains the profound, unanswered question resting upon the foundation of molecular fate.